So today we are beginning the new topic, okay, AC circuits. So let me introduce the basics of AC sources today, okay, before getting into AC circuits. So first we'll introduce you to AC sources. Then we'll talk about AC circuits built by using R, L, and C components. Then we'll see the analysis of AC circuits using basic laws, linear laws only, linear circuit laws in AC circuits. We'll see how we are going to apply all those laws into AC circuits. Okay, so two parts AC circuits. One is you need to understand better about AC sources. What is this AC represents? AC represents what? DC represents what? You know very well. What is DC? DC represents
Direct current,
direct current. AC represents?
alternating current,
Yes. Okay, so AC represents, usually I prefer DC means capital letters, AC means small letters. Okay, so alternating current. By default, AC means usually the one which is AC always take, for example, current. DC current means we used to represent by a capital letter. AC current means it's a current varying with respect to time. So we used to represent this by small letter. Any AC parameter have the habit of representing by small letter. Any DC parameter have the habit of representing by capital letter. Okay, so that notation already we are following everywhere. Once again, stressing on that. So alternating means it is by default it is going to be a sinusoidal. By default we call it as a sinusoidal current. It is a function of time, I of t. How we represent the sinusoidal means we represent this by its peak value, that is ip, and the negative peak also going to be minus ip. That's a standard way of representing any alternating. By default alternating means it is a sinusoidal source. Okay, sinusoidal source. So what is the power supply we are getting to our home? What is the power supply we are generating in generating stations? AC or DC? AC or DC? AC only. Okay, right? So by default, an AC means it is represented by a sinusoidal pattern. This is a sinusoidal signal referred by its IP into sine omega t. Okay, that's how we represent an AC signal, a current signal having a peak value ip, and the frequency information omega is equal to given by 2 pi into f, where f is representing how many cycles of your periodic signal per every second. So by default the supply we are getting to our home is a 50 hertz power supply. Okay, we'll talk about that voltage and current, all those things. Just I'm going to introduce AC sources today. So already, okay, direct current means you know it's a constant current. So anything constant, use a capital letter. The one which is changing with respect to time is fundamentally instantaneous. Any instantaneous signal should be referred by a small letter. Okay, so this is an alternating current, so that is changing with respect to time. Every time this x-axis is the time axis, y-axis is your current magnitude for every given instant of time. So we just keep on changing, so we use the instantaneous representation. Instantaneous for what? Current. So I of t we say. Suppose if it is a voltage waveform, instantaneous means we use to represent this by v of t. That's a voltage signal that will be referred by vp into sine omega t, where vp represents its peak value, representing both positive peak as well as negative peak. Okay, we'll talk about all those things. Let me introduce the basic of AC sources today. Okay, is this point clear, everyone? Is this point clear? Is right?
Yes, sir.
So before getting into AC sources, okay, so understanding of AC sources. So let us begin understanding once again a source, a general source, a simple DC source only. Just a quick review of your understanding, that will build everything. So let me give a simple DC source, an independent voltage source. having a battery of, for example, 20-volt battery, let me take. It is connected to a resistor of 10 ohms. A resistor of 10 ohm. This is a supply Vs of 20 volts. Now the source is supplying the load. That load is having a resistance of 10 ohm. Tell me what is the current supplied by the source? What is the current supplied by the source? Use your Ohm's law. What is that? Vs is equal to the current I into R in the given circuit. Yes. Yes. What is the current?
2 ampere.
2 ampere. Okay. Current is going to be 2 ampere. So Vs is known, R is known, I is equal to Vs by R. So it's 20 volt by 10 ohm. It's easy. So it is going to be 2 amps current. So hope the direction of current is correct. Yes. Direction of current is correct. Because this battery fixes this potential, the top potential positive, bottom potential negative, means this is the higher potential point, this is the lower potential point. The battery is assigning this is higher potential, this is lower potential. The conventional current flow is always from higher potential to lower potential. Okay, so this is how the current is going to exist. Okay, so as per the Ohm's law, okay, Ohm's law won't talk about the direction, only talk about the magnitude of the current. So you have to take it in the right direction. So it is always from higher potential to lower potential. Okay, or higher pressure to lower pressure. That's how the conventional flow exists. That's how we mark it. Okay. Now the next question is, tell me who is delivering power, who is absorbing power. Who is delivering power, who is absorbing power. In the given
Delivering
circuit,
power.
who is delivering power?
Voltage source.
Source is delivering power. Source is delivering power. Who is absorbing power? That's a passive element.
Resistor.
So the one which is delivering power, we call it as active element in the circuit. That is active element. The one which is going to absorb power, we are going to call it as a passive element. But remember that a active element still can absorb it, but whereas a passive element cannot deliver it, it can always absorb it. That's all. Okay, source is absorbed. Okay, source, sorry, the load is or resistor is absorbing. Resistor or load is absorbing power. So one is delivering whatever the amount of power it delivers, the other one is absorbing. The one which is okay absorbing, always we call it as the passive element, which is always absorbing it. Okay, but active element is capable of both absorbing as well as delivering, and circuit will decide it. Okay, who is delivering, who is okay absorbing. Okay, now the simple thing is this. So you know, okay, how to comment on delivering power and how to comment on absorbing power. Let me clear that point once again for the newcomers. The one which is delivering current at the positive terminal, okay, here the current is delivered. Here at the positive terminal, current is getting entered. So the current is getting delivered by the source means the positive terminal current is leaving. At the positive terminal of the source, the current is leaving. So at the positive terminal of the load, the current is entering. So at the positive terminal, if current enters, it is actually termed as absorbing. At the positive terminal, if the current is leaving, it is termed as what? Delivering power. Is it clear? Is this clear, everyone?
Yes, sir.
Okay, so that's a way to decide which element in the circuit is delivering, which element in the circuit is absorbing. Okay, so with this information, let us understand AC sources better. Okay, so the first question about AC sources is whether AC sources are capable of delivering power or not. Whether AC sources, okay, or how an AC source, how an AC source delivers power to the load. Yes, can anyone answer this question? How an AC source delivers power? So in this case, the last case, it's a DC source. It is having a constant voltage. If you plot this with respect to time, If you plot your Vs, suppose if we take Vs of t, assuming it is instantaneous, if you plot with respect to time, the moment you turn on the battery, the voltage always remains 20 volt. Getting everyone? For any time, the voltage will be maintained as 20 volt. Therefore, the current is, if you plot the current waveform against time, then the current I of t in the circuit is also going to be a constant with a current of 2 amps. So it is going to be a constant. So a constant 20 volt delivering constant 2 amps current. So resulting in constant delivery of power from source to the load. Agree everyone? Yes or no?
Sir.
Following right?
Yes, sir.
Okay, so the voltage is positive, the current is positive. Okay, as per the assumed direction. Therefore, the source is always delivering power, whereas the load is always absorbing power because the current is entering the positive terminal. Okay, but when it comes to an AC source, for example, let me represent an AC source like this. That's my AC source. The symbol represents its AC, but still habit is plus and minus to represent higher potential and lower potential. Okay, so that's a convenient marking, like how we represent our DC source. Even AC sources are designated with plus and minus in detail. Okay, we'll see. Okay, so practically it has to be mentioned by phase and neutral. Instead of that, let me take plus and minus, and still the notation is same, mentioning higher potential and lower potential points only. Okay, so now let me say this is V of t is equal to, that's a supply voltage, Vs of t is equal to, for example, 100 volt sine omega t. Okay, so omega t means I'll take omega equal to 100 pi into t volts. That's my input signal, source signal. It is, okay, represented by volts. That's a unit, or shortly I can say V also. Okay, but anyway, that V is already given. So instead of that, I can remove this V. Then shortly I can say it's 100 sine 100 pi t volts, I can say. Getting everyone? That's my signal. Okay. So if you plot the signal Vs of t for one cycle, okay, this is 100 pi. 100 pi is equal to 2 pi f, that is omega. Omega is 100 pi. Okay, that is equal to 2 pi f. So if f is equal to, then 100 pi equal to 2 pi f means, so 100 pi by 2 pi will be your frequency. Yes, I took frequency as 50 hertz. Okay, it's a 50 hertz means it is going to have 50 cycles in 1 second. 50 cycles in 1 second. Tell me what is the time period of one cycle then? 50 cycles it is going to have. It's a periodic signal. The signal is periodic. The AC sine wave is periodic. Okay, it is going to repeat its cycle after how much time? The time period I'm asking. So if you refer the basic of the time period of a periodic signal is inverse of how many
1 by
cycles it
50.
can do in 1 second. Yes, 1 by f shortly. So time period of a periodic signal. Periodic means its pattern is getting repeated, okay, after a finite time, that is t. Okay, so if you plot the signal can be plotted with respect to time like this. It's a periodic. So after every t, it is going to complete its cycle. This is 2t. So 0 to t, whatever the pattern it is having, the same pattern it is going to resemble for t to 2t as well. Okay, right? Nothing will change. Okay, that is what we call as a periodic signal. This is how we represent this signal. Okay, Vs of t with the peak of 100 volts. So I can say directly it is 100. Okay, so this is going to be, the maximum value is going to be 100, and the negative value maximum is going to be minus 100 volts. Hope it is clear, everyone. Yes.
Yes,
Yes,
sir.
sir.
Okay, so now tell me what is the time period of this periodic signal. And f is equal to 50 means it is going to be 1 by 50, okay, seconds. And put this in milliseconds. If you put this in milliseconds, you will get so 1 by 50 is nothing but 0.02. Then instead of 0.02, make it in millisecond, multiply by 1000 and put it in millisecond. Then the time period is equal to what? 20 milliseconds. So the t is going to be 20 milliseconds. So frequency, this is your AC source having a frequency of 50 hertz. that is going to have a time period of 20 millisecond, and the peak is 100 volt. Okay, so any AC signal, a sinusoidal source is referred by its peak and the frequency information. Okay, a better understanding. So how we define an AC source, we should know. So we need the peak information and we need its frequency. We need the peak information, we need its frequency. Then we can represent the instantaneous voltage waveform against your time. Okay, it's periodic, but I'm stopping at 2t itself. It is continuous. Okay, beyond that also for every t it is going to repeat itself. That's your Vs of t. Okay, the question is, when I connect such a source to a load, to a resistive load or simple resistor, we'll see how it is going to deliver power. Anyone tell me whether it is capable of delivering power or not? Because it is alternating. So when you refer the waveform, it says this waveform is having a positive value throughout this 0 to t by 2. So 0 to t by 2, if we take the time period between 0 to t by 2, your signal Vs of t is positive. If signal Vs of t is positive, if we take the time period between t by 2 to t, and it is having a negative value, okay, so therefore Vs of t is, so we call it as a positive off cycle of the sinusoid and negative off cycle of your sinusoid. So Vs of t is going to have negative value. Okay, therefore the AC source is going to have, for the first half cycle it is going to maintain a positive value, second half cycle it is going to maintain a negative value. The question comes whether it is capable of delivering power or not. Yes, anyone? Shaktivel, whether it is capable of delivering power? Yes, Sandil, capable of delivering power, AC source? Yes, whatever you feel you can convey. Yes, Anandi, Yashwant,
Sir, I think it can deliver power, sir, in both halves.
in both off cycles.
Yes, sir.
Okay, yes, anyone else? Yes, Fadil, what do you feel?
Can, sir. It can deliver power in
It can deliver power in?
both positive and negative cycles.
Okay, okay. So no problem because of the negative sign. Its value is becoming a negative during t by 2 to t. That's not an issue. Okay. Okay, Fadil?
Or it can absorb, deliver power in positive cycle or absorb power in negative, maybe like that also.
Okay, we'll see. Okay, right. So the simple question, your understanding about an AC source, before exciting any circuit using AC source, we should know first whether the AC source is capable of delivering power or not. Okay, once, okay, we conclude it is capable or not capable, then the analysis begins for the AC circuits. Otherwise, there is no meaning. Without understanding the source, okay, so we can't use that source for the application. Okay, because ultimately electric circuits are doing what? Electric circuits are simply, electric circuits are, what they perform. Electric circuits are simply processing energy. They are energy processes. Okay, so the signal source must be capable of delivering energy. We have electrical energy. Okay, that is the input to the electrical circuit, and that is going to convert into any other form of energy. It can be mechanical, it can be thermal, it can be audio, or it can be a video. Okay, any other form of energy it can perform. It can process that electrical energy and then give the result as any other form of energy. That is the purpose of electric circuit. So when excited by AC source, the AC source, if it is capable of delivering power, then we can treat this as capable of delivering energy as well. So that energy, electrical energy, can be utilized and then can be converted into any other form. Okay, if it is not delivering power, then there is no meaning. So that's a very purpose of, okay, the electric circuit. So it has to utilize the source of energy. That source of energy may be a DC source or the source of energy may be AC source. Okay, so when you talk about whether the AC source is capable of delivering power, and we know energy is the power supplied over the period. Okay, power supplied into the time period during which it is supplied, that is going to give the energy supplied by the AC source. We'll see first. That's why the question whether it is capable of delivering power or not. Once it is capable of delivering power, it is capable of delivering energy. That energy can be utilized and can be transformed into any other form of energy by using electric circuits. Is this point clear, everyone? Is this point clear? Yes.
Yes, sir.
Yes, sir.
So now we'll see. So let me have a simple AC source. Then why this convention plus and minus? Why this convention plus and minus? When I say plus and minus, okay, the representation is this. The signal is starting this way. When I say this way, minus and plus, then anyone tell me how to draw this? If I say minus and plus, then
First in negative cycle, then in
yes,
positive.
first negative cycle and then, okay, yes, you need to assume that this is like your reference. So this is like your reference that is connected to 0 volt. You are taking this as Vs of t. Then, so the reference is starting from 0. That's what it means. Okay, so during positive off cycle, this will be plus. But during negative off cycle, automatically this is going to be minus and this is plus. That's what it mean actually. Suppose if given this way plus and minus, so you have a phase shift of 180 degree. That's what it mean. Again, you are taking this as a reference. So this is your Vs of t, and since it is negative, it is beginning with the negative cycle. Since it is positive, it is beginning with the positive cycle. You can, okay, logically understand that way. Getting everyone? Getting everyone?
Yes, sir.
Okay. So let me take this. The convention also mentioned, sorry, explain why it has to be plus and minus. Usually that's a norm for a DC source. We follow the same thing for the AC source as well. The source is 100 sine omega t. Let me take. So here we are not concerned about the frequency. It's all about the peak value only. So many volts. Okay, that's a signal. I'm going to connect this to a load, a resistive load, a resistor, RL, RL we can say, RL we can say. Let RL is equal to, for example, a 20 ohm resistor. Okay. Now we'll see what happens during positive off cycles and during negative off cycles. Okay. So let me remove this minus and plus signs so that will conveniently play during positive and negative off cycles. So during positive off cycles, that is omega t is going to be between 0 to pi. That's one way. Or you can say your time period is between 0 to what? T by 2. Getting everyone? Either theta, this omega t is nothing but theta. So it can be treated as 100 sine theta. So theta, it has to be one cycle. So 0 to 180, it will be positive off cycle, and 180 to 360 degree, it will be negative off cycle. Shortly, let me say this is positive off cycle and this is negative off cycle. Okay. So let us do the analysis during positive off cycle. During positive off cycle, this is positive and this is negative. Taking this as a reference, that is 0 volt. Okay, therefore the signal at this point is going to have only positive off cycle. Okay, let me play at one point. Okay, so this is theta, so this is 0 to pi, so let me play at pi by 2, otherwise t by 4 we can say. This is t by 2 and this is t by 4. T by 4 is nothing but at time t equal to t by 4, it is nothing but theta equal to pi by 2. Okay, or you can also say at theta equal to pi by 2. Let us make a simple analysis in the circuit. At theta equal to pi by 2, tell me what's the voltage of the source. At theta equal to pi by 2, there is omega t equal to pi by 2. Sin pi by 2 is 1. So the voltage is going to be exactly 100 volt. Getting everyone? All of you getting? Following?
Yes, sir.
Anyone say yes? Fadil.
Yes, sir.
Okay. So then at theta equal to pi by 2, the voltage source is 100. Therefore, taking the bottom potential as 0, the top potential raises because this is lower potential and this is higher potential. Potential raises by 100 from 0 means the top potential will be 100 volt. Or exactly as per the waveform, this is equal to the peak value that is equal to 100 at time t equal to t by 4 or theta equal to pi by 2. So this 100 volt at this point of time. So therefore, this is also going to be 100 volt, and then the potential difference across. So this is 0 and this is 100. So 100 is higher potential, 0 is lower potential. 100 volt potential difference exists across 20 ohm. Will set a current of how much? Will set a current of Ohm's law.
5
100 by
amps.
20.
5 amps.
5 amps current. So what is the current we are talking about now is we are at the peak, okay, instant of your voltage. So current is also the peak current. Okay, so this is okay at theta equal to pi by 2, this voltage Vs is equal to Vp and this is your Ip. Okay, so this is the point. If you give a sinusoidal okay voltage having a pattern of this for 0 to pi by 2, and the current is going to have the same pattern. Okay, so but its magnitude is equal to what is its magnitude? So this is your voltage, another one is the current. Okay, this is your voltage profile and this is your current profile. Yes, what is the voltage profile at pi by 200? Current profile at pi by 2, 5 amps. Okay, so therefore it is going to follow the waveform same as your input waveform. So the current through the load resistor is going to be same as your input waveform, but its magnitude is current with a peak value of 5 amps at pi by 2, theta equal to pi by 2. Getting everyone? All of you getting this? Following, right?
Yes, sir.
Now tell me, I took one sample, okay, I took one sample to play at theta equal to pi by 2. It's a one sample of your positive off cycle. That's a maximum point in the positive off cycle. I took this as a sample to play what is happening in the circuit at this particular time. So tell me whether the source is delivering power or not. So you know the current direction. Now tell me who is delivering power, who is absorbing power. Polarity marking already mentioned for the potentials. Current direction also mentioned as per the potential markings. Yes, tell me who is delivering power, who is absorbing power. This is your source and this is your load. Tell me who is absorbing, who is delivering. Yes, everyone following, right? Is then respond. Your understanding, then you have to respond immediately.
Source is delivering and the resistor is absorbing.
Yes, at the positive terminal, the current is leaving for the source, whereas at the positive terminal, current is entering. Therefore, the source is delivering, whereas the load is
Absorbing.
Observing.
absorbing. So, source is delivering power and load is absorbing power. So, therefore, during positive off cycle, the AC source is capable of delivering power. Okay, that's a conclusion. How an AC source delivers power. Already it is giving the hint. Okay, it is going to deliver power. You need to understand how it is delivering power. Okay, so it's confirmed During positive off cycle, an AC source is capable of delivering power. So power flow happens from the source to load. Power flow is from source to load. We'll see what happens during negative off cycle. Okay. So during negative off cycle, we'll see what happens. Again, so set the problem at theta equal to 3 pi by 2, that is 270 degree. So this is your theta. So sine 270 is minus 1. Sine 270 is minus 1. Therefore, this potential is going to be minus 100. So this is still plus and minus I'm saying, but I'm saying this battery voltage is equal to minus 100. Tell me what is your perception immediately. What it mean? I'm giving you the battery like this. I'm saying this is a battery. I say this is plus and this is minus, but here I say it's a minus 5 volt battery. Then tell me what's your understanding. If I say plus 5 volt, the designation top plus bottom minus is valid. If I say minus 5, what is that? If I say minus 5, so I say that by giving minus 5, what I say here means I say the potential difference across this, which you designate earlier as plus and minus, then this potential difference I'm giving as minus 5. What it mean? What it mean? Your assumption is wrong. Okay, it is existing in the opposite direction. So effectively what it means this is actually minus, this is actually plus, then you have to take this as plus and this is minus, then say with the positive it is 5 volt. That's what it means. By wrongly mentioning the top as positive and bottom as negative, okay, you're giving minus 5, okay, that says your assumption is wrong, your polarity markings are wrong because of this minus 5. Okay, otherwise you need to feel this way. Okay, to make it simpler, so top potential you can call it as VA and bottom potential you can call it as what? VB. What I'm saying here is VA minus VB is equal to minus 5. Instead of that multiplying by minus, I can also say VB minus VA is equal to what? Plus 5. What it mean? Your B is higher potential, A is what? Lower potential. So this is the point A and this is the point B. That's what I'm doing finally. So B is higher potential, A is lower potential. That difference is equal to 5. Getting everyone? So finally I say this is plus and minus. So the moment by giving plus and minus, if we have a negative sign, it means that you need to reverse your marking. Understood everyone? Following this?
Yes, sir.
So initially it is given this is plus and this is minus, but this signal takes a value of minus 100 at theta equal to 3 pi by 2 means that is 270 degree means what is the real thing? This is not the real thing. What is real? What is real? All of you getting? Then it has to be positive. It has to be negative. Are you getting? All of you getting this point?
Yes, sir.
So then taking this as 0 volt, okay, analysis only at one particular sample of your negative off cycle. So this is your negative off cycle. We are here. Okay, so we are here. We are at minus 100 volt point in the negative off cycle. Okay, so we'll see what is happening to the current. Is tell me what's the current direction. Current direction, please. So what is the top potential, anyone? Top point potential, please. The bottom, I'm taking it as a reference of 0. Tell me what is the top point potential?
minus 100.
Minus 100 volt. Because the potential decreases. This is higher potential and this is lower potential. We are moving from higher potential to lower potential means subtract from whatever your higher potential you have given 0. Then lose 100 from 0. So you'll get minus 100. So this point is going to be minus 100 volt. That's what the source is doing. Source is fixing this as minus 100 and this is as what? 0. The source is fixing. Who is higher potential now? Minus 100 or 0?
0 volt.
0 is higher potential. Minus 100 is lower potential. What is the net potential difference? That's the right polarity marking like this. Okay. Yes. What is the difference? This potential minus this potential. Here this is A and this is B. So VA minus VB. VA is 0 volt, VB is minus 100. So VA minus VB is going to become what? 100 volts. Now tell me what's the current in the resistor. What is the current in the resistor?
5
amps. In
5
which
amps,
direction?
5 amps.
Yes, in which direction? That's a question.
Higher potential to lower
Higher
potential.
potential to lower. Therefore, the current is going to exist in this direction. Correct? Okay. So then it is going to be 5 amps current. Now tell me what the source is doing and what the load is doing. Yes, Monisha following?
Yes, sir.
Yes. Sendil, what source is doing, what load is doing? Yes, Bonapriya, you can also say.
Source is absorbing,
Source is absorbing. Load is?
delivering, sir.
Okay. So let me get the confirmation from Anandi.
Sir, source is
Yes, Swati, you can also say. Sources?
source is delivering, sir, but
Source is delivering.
resistor is absorbing, sir.
Load
Resistor
is
cannot
absorbing.
deliver.
No, we should not go by that. Okay, we know that resistor should not deliver. Okay, we should not decide based on that. So based on the current entry to the plus terminal and current leaving at the plus terminal, you conclude. That's the only point you need to stick to. So the positive terminal, current should enter, current should leave. So for source, current is leaving the positive terminal or entering the positive terminal. For the resistor, whether the current is entering the positive terminal or leaving the positive terminal. That's all we need to focus. Yes, Dinesh, you can also say.
So
With this knowledge.
source is absorbing and load is delivering.
Okay, source is absorbing, load is delivering. Okay, how have you concluded this, Dinesh?
So because in load the current enters positive terminal and
In load, current enters positive terminal means it is absorbing, right?
sorry sir leaves.
Getting the point? Yes, the
Yes, sir.
current is entering the positive terminal in the load, whereas in the source, current is leaving the positive terminal. Agree?
Yes, sir.
Then
Yes,
what
sir.
source is doing?
Delivering.
Delivering. Getting, Dinesh?
Yes, sir. Yes, sir. Sorry.
Yes. Source is still delivering. Getting, Bhanupriya?
Yes, sir.
So you're seeing this point, but see that point, its entry point is negative. But we don't comment because to keep the convention simpler, we refer only the positive terminal point, higher potential point. At the higher potential point, refer what is happening in the source and refer what is happening in the load. In the load at the higher potential point, current enters, so it absorbs. Okay, and this is delivering. Getting? Easy, Bhanupriya? Getting?
Yes, sir.
Okay. Is the point clear? So source is not absorbing, load is not delivering. Okay, so the point is, okay, load is absorbing again and the source is delivering. Okay, is the point clear, Swati?
Okay.
Yes.
Yes, sir.
Okay, yes, source is still delivering even though we are in negative off cycle. So I took one sample in the negative off cycle. The source is still delivering power, the load is still absorbing. So irrespective of in which cycle you are, you can be in positive off cycle or you can be in negative off cycle. So you have to believe first an AC source is capable of. An AC source is capable of. Yes,
Delivering power.
always. Correct? In any time over the complete cycle, it is always capable of delivering power. The source, even though it is having alternating, okay, current, it is delivering alternating current, it is having alternating voltage signal, which is having positive off cycle and negative off cycle. It doesn't mean that it is going to deliver power in the positive off cycle. It is going to absorb power in the negative off cycle. If that is the case, the net power delivered by your AC source will become zero. Because whatever the power delivers, it is delivering during positive off cycle. If we feel it is absorbing during negative off cycle, whatever delivered it is going to absorb. That means the net power delivered by the source will become zero. So the AC sources will do nothing in the load. Okay, they will never deliver any energy. So the important convention here is, important understanding here is, okay, 1 minute. Yes. Let me continue. The point is this. Okay. The important understanding here is irrespective of the cycle, the source is delivering power. It is always delivering energy. Okay. Anyone having doubts in this understanding? Hope it is clear. Yes.
Yes,
Yes,
sir.
sir.
Clear.
So it is capable of delivering power. It is capable of delivering energy. Okay. Throughout this period. Okay. So yes, this is what we need to believe first in an AC source. Okay. So now we can believe AC source is delivering power. Now, can you tell me how much power it is delivering in the circuit? Yes. Let me take this. This is plus minus. Tell me what is the power delivered by the AC source. This is your Vs of t. Let me take. Okay, this is delivering the current I of t. Okay, right? Assuming it is delivering the power, the instantaneous power it is delivering is Vs of t into the current it is delivering I of t. I'm assuming it is a power delivered. Okay, so I took the current, it is leaving. Since I said delivering, so let me take the current direction that way. So power delivered or power delivering by the, better you say power delivered by the AC source. Instantaneous power only I'm talking about. That's instantaneous power delivered by the AC source. Okay. Yes. You know the current or the peak current. So the peak voltage is 100. So 100 by 20 is 5. So the peak current will be 5 amps. So it is going to be 5 sine
500.
omega t amps. Getting everyone? That's an instantaneous current, okay, through the load. Now tell me what is the instantaneous power? The instantaneous power is equal to, yes, the instantaneous power is equal to
500.
100 sine omega t into what? It is volts, remember? And 5 sine omega t. The result is going to be, this product is going to be volt into amps. And volt into amps is equal to, volt into amps is equal to watts. It's going to be in power unit. Okay, V into A. Okay, in DC, that's how we have the convention. We'll see. Okay, how we are going to play in AC circuit. This is the power. Okay, instantaneous power delivered by the AC source. Then I can say the instantaneous power P of t. It has to be small. Remember that. Don't use capital P. Use small p. Okay, so I small I, V small v, and P also should be small. Okay, instantaneous power delivered by the source, AC sources, 500 sine square omega t. Okay, volt amps or watts you can say. Okay, better let me call it as volt amps. Okay, all of you getting? All of you getting this?
Yes, sir.
Yes, sir.
Then what will be the waveform of this instantaneous power? How the waveform will look like? It's a sine square waveform. It is a sine square waveform. So if you plot this waveform P of t, if you plot this waveform P of t, yes, what is the P of t? Instantaneous over any time period. It is 500 sine square theta. Let me take. Okay, so let this is theta. Okay, so now for every theta, let us go for one cycle at least. The one cycle is still 2 pi. Okay, so at pi, what is the power? Tell me at pi, what is the power it is going to deliver? At 0, theta equal to 0, what power it is going to deliver? At theta equal to 0, what power it is going to deliver? Otherwise, you can take a simple table, theta and power of theta. Let me go with. That's instantaneous power for every theta instant from 0 to 360 degree. Okay, so let me take 0 degree. Okay, 0 in radians. Okay, pi in radians, then 2 pi. Yes, now at 0, theta equal to 0. What is that?
0.
It is 0 watts. We can say pi.
That is also 0, sir.
Yes, 2 pi.
0, sir.
Yes, then. Clear everyone? All of you getting?
Yes, sir.
Okay, then at pi by 2 and 3 pi by 2. That's a peak point of positive of cycle, peak point of negative of cycle. Yes. So sine pi by 2 is
1.
its square
1, sir.
1. So what is the resultant?
500.
Yes, then 3 pi by 2. What is sine of 3 pi by 2? Minus 1. Its square?
1.
1. So what is the net power?
500.
500. Okay, so that means if you plot this waveform, power of theta, the instantaneous power profile of your uh, power delivered by the source, AC source, if you go for this, if you plot it, if by taking few more samples between 0 to pi and pi to 2 pi, I took only one sample. If you take this, then the waveform will look like this. The waveform, instantaneous power profile waveform will look like this. Okay, with the maximum of, you try this for a few samples, then you will understand. Okay, something similar to this. Okay, so the peak is going to be 500. That's a peak power, we can say. The peak power is 500 watts, we can say. Then it is going to repeat the pattern. So interestingly, the power is going to be periodic only with respect to what? The power flow is periodic with respect to pi itself. Getting everyone? All of you getting? Following, right?
Yes, sir.
It's going to be something like this. Okay, so make it symmetric with respect to this point. So left side and right side will be the mirror images, and here also the left side and right side will be the mirror images. So this is pi by 2 point, and this is 3 pi by 2 point, and this is pi point. So 0 to pi itself is going to be the period of the power signal. Okay, so if a signal is having, okay, so T as a time period, if you go for the power delivered by this, the frequency of the power delivered will become double that of your signal frequency. Okay, so this is 0 and this is T by 2 and this is going to be T, means the frequency becomes, sorry, the time period becomes off for this periodic signal. Therefore, the frequency is going to be double. Getting everyone? Yes or no? Someone may ask you what is the frequency of your instantaneous power. Okay, then it's a double that of, because of sine square, because of sine square. Okay, if it is sine omega t, then if it is sine square, then you can convert that into, okay, so corresponding double the frequency form. Okay, you know the corresponding equivalence. Okay, we'll see that. Okay, that is what we are going to see next. So that's instantaneous power profile delivered by the source. So the power is always positive. Yes or no? Yes or no?
Yes, sir.
So this is another way of proving it. So the power, instantaneous power, is always going to be positive. The reason is, when voltage is positive, current is positive. When voltage is negative, the current is also going to become negative, and the product voltage and current is always going to be positive. Therefore, the power is always, power delivered by the source according to the convention is always going to be positive. So that's a simple way to take things granted. Understood? Getting everyone? Following, right?
Yes, sir.
Yes, sir.
Okay, so yes, we'll go ahead. So what power we are going to talk about
Yes, sir.
means, so power delivered, first we talk about the instantaneous power. Okay, but instantaneous power is not a constant value. There is always going to change. Okay, but still we need to talk about the power. What power we are going to talk about in AC circuits means, in general, what power we talk about means, we talk about average power only delivered by the sources. But when it comes to DC, the voltage is constant, current is going to be constant, the power profile also going to be constant. That is going to serve as the average power. So whenever you talk about power of a periodic signal, we talk about power of a periodic signal means it is always going to be, by default, power means it is talking about only average power. Getting everyone? All of you getting? Yes. So we'll talk about what is the average power delivered by an AC source. Average power delivered by an AC source. Okay. So tell me what's average power delivered now. We're going for the average power now. So what is the average power? The average power is P average. So it's average of this over a period. Average of this power profile over a period of your signal. What is the signal period? 0 to T only. So therefore, let me go for the average power over a period 0 to T. But you need not to go for 0 to T. You can stop the problem at T by 2 itself. You know the reason now, because of this graphical representation. All of you getting? Yes, right? Because the profile of the power is same. Okay, whatever the profile it is having from 0 to t by 2, it is having the same profile from 0 to, sorry, t by 2 to t. Getting everyone?
Yes, sir.
Or you can say whatever the profile it has from 0 to pi, it has the same profile from pi to 2 pi. So therefore, you need not to make the averaging over a period t, but you can make the averaging only over a period t by 2. Whatever the average it is going to make for this period, it is going to make the same average for the next period also. Getting everyone? All of you
sir.
getting this point?
Yes,
Yes,
sir.
sir.
So that's what the P averages. We'll see how we can find it. So P average in general, if you go for average of any signal, any periodic signal, average of any periodic signal, for example, I have an instantaneous voltage V of t defined as Vp sine omega t means, then if I want to find its average, so I call it as V average. Then I go for averaging over a period. So integrate that profile over a period, then go for averaging. So this is your area. Okay, 0 to integral means area you have to take. So integral of your V of t with respect to time. So what's the area of your voltage profile over a period? Then go for your averaging. Okay, so get the total area and average it with respect to time. That's how we get average for any signal. That's averaging concept, average of any instantaneous periodic waveform. Similar to that, here we talk about average of your power. So if that is the case, again over a cycle 1 by t. So it is 0 to t, and what average we are looking for? Power only. So take the instantaneous power and profile with respect to that. Then this becomes average power is equal to 1 by t by 2, and 0 to t by 2. Let me take power of t with respect to time. The result is going to be same because it's periodic with respect to t by 2. Getting everyone? Yes or no?
Yes, sir.
So like that, we can quickly conclude. So instead of this, I can take P average is equal to, it's 1 by pi, because instead of t by 2, let me prefer pi, an integral 0 to pi. Okay, so the instantaneous power of theta and d theta, let me do shortly. So then the average power delivered by the source over a period 0 to pi is going to be the same for pi to 2 pi as well. So then 0 to pi, and it is 500 into sine square theta into d theta. Getting everyone? Following this?
Yes, sir.
Yes, sir.
Then tell me what is sine square theta. So we need an identity. Sine square theta can be written as 1 minus. Is it true?
Yes, sir.
Okay, exploiting this understanding, it's 1 minus cos 2 theta by 2, then replace your sine square theta. Okay, then this integration becomes, so take 500 out, so it is going to be 500 by pi. Okay, integration 0 to pi, replace sine square theta by 1 minus cos 2 theta by 2. Okay, integration with respect to theta. Then this average power delivered by the AC source becomes 500 by pi. That's common. This is divided into two parts. One is, let me take 2 also out, make it 2 pi. Okay, as common. So then first integration is 0 to pi. That is 1 into d theta minus another integration is 0 to pi. That is cos 2 theta into d theta. Getting everyone? All of you getting this?
Yes, sir.
Okay, then perform the integration. Then the average power is going to be, average power delivered by the AC source is going to be 500 divided by 2 pi. Then first integration, integration of theta, d theta, integration
Theta.
of d theta,
Theta.
theta. So
Theta.
upper limit is pi and lower limit is 0 after the integration. Then integration of cos 2 theta
1 by 2 sine 2 theta.
plus or minus, integration of cos theta
That's only, sir.
plus only, right?
Yes, sir.
Okay, so the minus sign will stay. So then cos 2 theta becomes sine 2 theta by 2. Getting everyone? All of you getting?
Sir.
Upper limit pi, lower limit 0. Then when you substitute the limit for your sine n theta, here's sine this one. What is the resultant? Sine n theta always is equal
0.
to sine n theta. Okay, so this sine n theta where theta equal to pi is sine n pi. Let me take sine n pi always equal to
0.
0. So therefore this will never yield any result. Therefore this is the only one going to contribute for the average power delivered by the source. So what we get is 500 by 2 pi into this is going to be pi minus 0. So it's only pi. So what is getting cancelled? Pi and pi will get cancelled. 500 by 2. What is that?
250.
The watts is the power delivered to the load. Getting everyone?
Yes,
If you're
sir.
getting this?
Yes, sir.
So this is what we call as average power, okay, or effective power delivered by the source. We call it as effective or average power delivered by the AC source. Average power delivered by the AC source. Hope it is clear, everyone.
Yes, sir.
Okay, so this is effective. That's an important term. Okay, going to make things even effective. Okay, so that's effective. What is this effective power? What is this effective power? Anyone tell me what is this effective power? Average power. I said effective power is nothing but average power. What is that effective power? Why I use the term effective? Yes, anyone? So now you will understand. Suppose if I play like this, what is mean by an effective power? We'll see. This is V in of t. That's a supply. Let me take. That is Vp sine omega t. And this is connected to the load. There is a resistor. Let me play theoretically. This is R. And this is going to be the current I of t. I of t is your V in of t divided by instantaneous voltage divided by resistance. It is going to be Vp sine omega t divided by R. Now, if you talk about the power delivered to the load or power delivered by the source is nothing but, yes, it is V in of t into I of t. That's what you're going to get, which is nothing but I of t is known, V in of t is known. Then what you're going to get is Vp sine omega t the whole square divided by R. Agree everyone? Following this? This is voltage and this is your current. Just get the product of the two. All of you getting this?
Yes, sir.
Now tell me what is average power. Then if you talk about average power, so this I can say it is Vp square divided by R into sine square omega t. Then you can say it is sine square theta. Then average power is equal to, again, it is going to be a periodic with respect to pi itself. So 1 by pi integration 0 to pi only for that period. Then you get Vp square by R into sine square theta into d theta. Then what is common? Vp square by pi into R will be common. Rest is what? Integration 0 to pi sine square theta into d theta. Now let me take this as an identity based on the last result. So this is where we had our, okay, integration of sine square theta d theta, that is resulting in this, that is resulting in this, that is resulting in this. What is that result? It's only pi. All of you getting?
Yes, sir.
All of you getting?
Yes, sir.
So shall I conclude this as an identity? Integration of integration of your sine square theta over a period 0 to pi with respect to theta will yield the result of only pi. Shall I take this as an identity as per the last experience?
Yes, sir.
Yes, sir.
Okay, so by taking this directly here, we can conclude is then what we get is from this, let me conclude here itself. Okay, so let me conclude P average is equal to what is P average? Yes, conclude P average. Vp square divided by
R.
pi into R. This is concluded as what? Pi. So multiply by pi. Pi will get cancel. All of you getting?
Yes,
All
sir.
of you getting this?
Yes, sir.
Yes. What we missed on the way? We missed
1 by
something.
2, sir.
Yes, we missed something because on the way we took 2 out, right? This 2 out, okay? That 2 is outside. Therefore, I should conclude this as only pi by 2. Getting everyone? All of you getting? Yes or no? So this is pi by 2 only. Getting everyone? I should not say here pi because 2 is taken out. I should not say here as pi by 2. So therefore the whole is, this is the identity. Okay. We don't want to do it again. That's why. Okay. We are trying to exploit whatever the understanding we had earlier. So it's pi by 2. All of you getting? Yes or no?
Yes, sir.
So then take pi by 2 as this identity. So this is pi by 2. That's a mistake. So then pi by 2, pi will get cancelled. Take this as an identity hereafter. But the limits are 0 to pi only, not for 0 to 2 pi. Okay. 0 to pi only. Then it is pi by 2. Then exploiting this directly, one can say it is Vp square by what? Vp square by
R.
2R. Vp square by 2R. Therefore, the average power delivered by any periodic AC sine wave is equal to Vp square by 2R. That is what the power we are calling it as effective power delivered by the AC source. Why that effective power? We'll see. The proof is not yet given. Okay, that's an effective power or average power. Hope it is clear theoretically. So now you know the moment I give an AC source of Vp sin omega t, omega is not in the play. Okay, so only the peak value in the play and the resistor is in the play. So Vp square by 2R is the power delivered by the AC source. Is it clear?
Yes, sir.
So now let us make a simple comparison. So let us compare this power with the power delivered by a DC source. I'm giving AC source delivering power to a resistor R. And this is the signal Vp sine omega t. That's your source. Plus and minus. This is AC. Let me have a DC on the other hand here. Call it as VDC. Delivering power to a resistor. So we know the DC power delivered by the source. Tell me what is the DC power delivered by the source? By this source. What is the current? You know VDC by R, correct? This is plus minus. So the voltage across this is VDC. The current is going to be VDC by R. And what is the power? V into I. So VDC into VDC by R. The result is going to be V square DC by R. Agree everyone? All of you getting?
Yes, sir.
Instantaneous power is going to be your average power because nothing is instantaneous. This is a constant. This is a constant. Voltage is constant. Current is constant. It's not a periodic signal. It's a signal forever from time t equal to 0 to infinity. Therefore, this is the constant power it is delivering. We can also call it as average power, but nothing like average. Average for DC doesn't make any sense. That's a constant power it is always delivering the moment you turn on your DC powered supply. Okay, so that's a effective power we can say delivered by the DC source. That's a power delivered by the DC source. Let me call this as power delivered by DC source. Power delivered by DC source. Now you know the power delivered by the AC source as well. Tell me what's the power delivered by the AC source? The power delivered by the AC source, let me put PAC and this is power DC. Yes, what's the AC power delivered by the source? Vp square by 2 times your R. Agree? Yes or no?
Yes, sir.
That's what we concluded. It is Vp square by 2 times R is the power delivered by the AC source. So now we can compare the power delivered by the AC source with the power delivered by the DC source. But I want to make my AC power delivered as effective as DC. I want, understand this point, everyone? I want to make my AC power delivered as effective as my DC source. All of you getting? All of you getting?
Yes, sir.
Then I'm going to compare this with, so I'm going to make the power delivered by AC source as effective as DC means I want to make this as a function of a voltage called V effective square divided by R. So that V effective is nothing but the effective value of my AC source as effective as DC. As effective as DC. Getting everyone? All of you getting?
Yes, sir.
Yes.
So I want to get the value of AC source as effective as DC means I want the AC source to have a value, effective value that is as effective as my DC. Say for example, my AC DC source is having a 100-volt battery and resistance is equal to 20 ohms. Okay. Yes. What is the current DC current in this? 5 amps. Tell me what's a DC power straight away. 100 into 5. How much?
500
500
watts.
watts.
500 watts of DC power delivered by the source. Can you tell me what is my AC signal that will deliver same power as the DC source? Give me the value of AC signal which will deliver the same power like your DC source mean. That is what the value of the signal we call it as V effective. So tell me what is V effective of this AC source means. That V effective is as effective as your DC means. V effective as per the comparison. Tell me, compare the two equations. Then tell me what is V effective. Tell me what is V effective. V effective square is equal to Vp square by 2. Agree everyone?
Yes, sir.
That means tell me what is V effective. V effective must be equal to Vp by root 2. All of you getting? Yes or no? Following right?
Yes, sir.
So if I'm calling this source by a value of a source, AC source by V effective, I'm going to designate any AC source by its effective value. That effective value is going to deliver the power like your DC source. In DC source, we keep the equation simple V square by R, V square DC by R. Similarly, if V effective of an AC source is given, I can directly calculate the power as V effective square by R. All of you getting this point? All of you getting this point?
Yes, sir.
Now I want to deliver the power like the DC source, as effective as my DC source. Tell me what should be the effective value of this AC source. I want AC power to be 500 watts like my DC source. So tell me what should be the V effective. V effective value should be same as VDC. All of you getting? Then only it will deliver same power. Yes or no?
Yes, sir.
Then what is VDC? 100 volt. So what should be V effective?
100 volt.
Yes. Therefore, the AC source should have a V effective of 100 volts. So V effective of AC source should be same as your DC. If that is 100 volt, the AC source will deliver same power like your DC source. All of you getting this point? All of you getting this point?
Yes, sir.
Okay, so what is that V effective? So V effective of an AC source is equal to 100 volt, but V effective is equal to what? Vp by root 2. That is equal to 100 volt means if an AC signal is having a value of peak value of 100 into root 2 volt, it will deliver the power like your DC source. That's what it means. Getting everyone? Following right?
Yes, sir.
Okay, so we call this as effective value. We'll see how you're going to find this effective value. Okay, so this V effective is equal to Vp by root 2. So if the effective value of AC source is same as your DC, then whatever the power delivered by AC source will be identical to the power delivered by DC source. That's what we call as effective power. That's why I'm using effective power. Effective power is because of the effective voltage. The effective value of voltage source, AC source, is always Vp by root 2. So therefore, hereafter, any AC source should be represented by its effective value. Getting everyone? All of you getting? Yes or no? If V effective is equal to 100 volt, if it is connected to a resistor, then directly we can say its power is equal to R is equal to 10 ohm, means 10 or 20 we used. 10 or 20 we used.
20, sir.
20. Okay, R is equal to 20 means directly I can say the power delivered by the AC source P average, or the power delivered by AC source, or power effective, is equal to V effective square divided by R, I can say. Getting everyone? Directly you can play like a DC. So directly you get your V square effective and divided by R. Then what is your answer? Then average power directly can be calculated as 100 square divided by 20. That is 10,000 by 20. You will end up with 500 watts of power, similar to the DC calculations. Getting everyone? All of you getting this? Following or not?
Yes, sir.
So we'll talk about that V effective. So V effective is the designation for the AC source, or this is how we wanted to represent an AC source. Any AC source must be referred by its effective value. We'll see what is meant by effective value now. So first confirm everyone. Hope you're following till this point. All of you.
Yes, sir.
Yashwant,
Thanks, sir.
Fadil.
Sir,
Okay, okay. So we'll see what is the effective value of an AC signal. Yes, if you have any doubts, if the mic is not working, you can also use the chat window. Okay, we'll talk about, yes, fine.
ಸನ್ನಿಹಿತ ಕಾಣುತ್ತೆ. ಪಾಠ ಬಿಡಿಸ್ಕೊಂಡು
So we'll talk about effective value now. Value of a signal, sinusoidal signal. Okay. So in the average power, how we calculate the average power? The average power is equal to 1 by T integral 0 to T. Okay, when the AC source is delivering, imagine the AC source is delivering power to a resistor. Okay, under the situation, I'm writing the average power conventionally. Yes, what is that? What is the instantaneous power P of T into dt? So what is that? 1 by T integral 0 to T. I'm going for the whole period. What is P of T? Your supply voltage, that is V in of T, or V of T we can say. Okay, let me take V in of T, and the current is going to be V in of T by R. Getting everyone? Yes, exploiting this, it is going to be instantaneous power is going to be V square in of T divided by R into dt. All of you getting this? Yes.
Yes, sir.
Then this average power is equal to 1 by T. Okay. Otherwise, let me take 1 by R. This 1 by R, what is the remaining? After taking 1 by R as common, what is the remaining? The remaining is 1 by T integral 0 to T V in square of T into dt. All of you getting this? Following?
Yes, sir.
So this average power we know is 1 by R into V square effective. Agree everyone? Following? As per the earlier conclusion. Now tell me what is V square effective. These two are identical. Both are talking about average power. Therefore, what is V square effective? Is equal to this. Getting everyone?
Yes, sir.
So therefore, I can conclude that's what the effective value I'm going to calculate with this understanding. What is it? V effective of an AC source. So V square effective is known now. Therefore, V square effective is equal to V square effective is equal to 1 by T integral 0 to T V in square of T into dt. Okay. Not to forget that already we have 0 to pi. Okay. 0 to pi sine square theta into d theta is equal to pi by 2. This identity we have. It's proved already. Okay. So you can also write this. Okay. V in square of T. Square of V in. So V in of T is given as V in of T is given as Vp sine omega T. Correct? Periodic signal, right? Yes or no?
Yes, sir.
Okay, that's a periodic signal defined over the period 2 pi. Okay, that's Vp sine omega T. If you square the signal, what will happen? If you square this, tell me what is V in square of T? V in square of T, it is going to become Vp square into sine square omega T. Agree everyone? All of you getting?
Yes, sir.
Okay, if that is the case, Vp square sine square theta is going to be periodic with respect to what? Pi itself. Yes or no? Instead of 2t, instead of t, you can go for t by 2. So therefore, v in square is going to be, the sine square signal is going to be periodic with respect to of the period itself. Exploiting this, I can write v square effective as what? 1 by pi integral 0 to pi. Then what? V in square of t as vp square into sine square theta into d theta, I can write. Agree everyone with this? All of you agree with this?
Yes, sir.
Then tell me what is the resultant. You get Vp square by pi. The remaining is 0 to pi sine square theta into d theta. And you know that identity already exploited. Then V square effective is equal to Vp square by what? Pi into what? Pi by 2. Pi will get cancelled. Makes that's a proof mathematically. Already we took this assignment here. What is the assignment here? Already we took the assignment here. So V effective square should be equal to Vp square by 2. Already we took. I'm giving that proof mathematically. All of you getting? All of you getting this point?
Yes, sir.
So hereafter, what is your conclusion? Yes. So this is giving a practical meaning of V effective. Okay, so that's analytical meaning of V effective. V effective is a practical meaning. So the theoretical effect of V effective you are understanding. So therefore, hereafter I can say that V square effective is this. Okay, that is reducing into what? Vp square by 2. Getting everyone? Correct? Following right?
Yes, sir.
So from this we conclude V effective is equal to, yes, V effective is equal to V, once again let me copy this. V square effective is equal to 1 by T integral 0 to T V in square of T into dt. Okay. So this one you can call it as, what does this mathematically means? You are squaring the signal. That's all. This is squaring the signal. Okay. And going for the average. You are getting the square of a signal and then going for averaging. This is averaging or mean, you can say. Getting? So first square the signal. If you square the signal, so what is the speciality of squaring the signal? So the normal signal is this. That is having positive off cycle and negative off cycle. If you go for averaging of this signal, simple V in average, that is not going to exist. It is going to be 0. All of you getting? All of you getting this point? Yes or no? What will be
Yes,
the
sir.
average of a periodic signal having positive off cycle and negative off cycle? Suppose let me go for this signal. This is my V in of t. So V in of t is equal to what? Vp sine omega t. Vp sine omega t. Let me go for this average, normal average. V in average is equal to 1 by t, integral 0 to t, then V in of t into dt. That's a normal average. So here we are going for the squared average, squared mean or squared average. So this is a normal average. So then if you integrate this over this period 0 to t, and integration is nothing but the area. So you're going to, you can also write V in average as what? V in averages 1 by 2 pi integration of your signal over a period 2 pi. Then you can say Vp sine theta into d theta integration with respect to this. But if you integrate the sine theta over a period 0 to 2 pi, it is going to be the area, whole area under this, and that is going to have area of positive of cycle, that is going to have area of negative of cycle, but the positive of cycle area will be cancelled by negative of cycle. Therefore, this result is always 0. All of you getting? That's what I'm saying shortly here. Is it clear, everyone?
Yes, sir.
Okay, therefore, if you take a pure sinusoid, if you go for a normal average, the pure sine signal always give zero current. Sorry, zero voltage. Even if you take a current profile, its pure average is going to be pure sinusoidal average for current or voltage will be zero only. Okay, that never exists. But if you go for squaring it, if you square it, the positive of cycle square you get, negative of cycle square also going to become positive. Therefore, average will exist. Getting everyone? All of you getting? Yes or no?
Yes, sir.
Yes, sir.
So you're going for the squared mean. The normal mean is not going to exist. You're going for the squared mean. Square of a signal is going to be voltage square. And this is going to be the mean. So it's going to be in voltage square. The whole is going to be in voltage square. Yes, left hand side is also voltage square. Okay. So it's a squared average or squared mean that will exist. That will exist. Okay. That will exist. And then finally, what is your V effective from this? What is V effective? Yes, root of V effective is root of 1 by t integral 0 to t what? V in of t square into dt. All of you getting this? That's your V effective. Okay. So we know that it is equal to V square effective is equal to Vp square by 2. Therefore, what is V effective? Therefore, V effective is equal to V effective is equal to all of you getting
Yes, sir.
Vp by
Root 2.
Vp by root 2. That's what we are going to get. So V effective is going to be Vp by root 2. So the effective value of an AC source, which is not having normal average, its normal average is 0, but it is having a squared average. So that is the one responsible for delivering power. Therefore, it's mandatory to represent any AC source by its effective value. But we don't remember it as the effective value, but we remember by the square and this mean and this R, then we call it as RMS. Understood, everyone? All of you getting?
Yes, sir.
Yes, Swati getting this?
Yes, sir.
Dinesh following this?
Following, sir.
Okay, so that's a convention. We remember RMS, we forgot V effective. So V effective makes a lot of sense, but VRMS talks about mathematics. How to get the effective value of an AC source. So RMS will say square the signal, apply the mean, and then apply the root. Okay, then RMS will give the effective value of an AC source. With that, one can quickly find its effective power delivered by the AC source. Okay, getting everyone? Directly V square effective by R. So because of this, okay, we have an habit of representing any source by its effective value only. There is nothing but its RMS value. Understood? Is it clear? All of you getting?
Yes, sir.
Sir.
So what is the power supply we are having in our home? In our home, we have a single phase, 230 volt, and what?
50
50
hertz.
hertz power supply in our home. That's a power supply energizing all our electrical appliances or equipments AC, washing machine, TV, whatever it is, okay, excited by this supply only, including your mobile charger, excited by this only. So where you have the relevant information, that is 230 volt. What is this 230 volt? This is how we represent our AC source, having a phase and neutral. Phase and neutral, any one of the three phases. It can be R phase, it can be Y phase, or it can be B phase, three phase. Assuming you have your home is excited by a three phase power supply, okay, then you will have one of the three phases, okay, to connect it to your uh, desktop or laptop. Okay, so this is what we designated as plus, and this is minus, that is represented by 230. What does that 230 means? It's VRMS only, or it's V effective only. The effective value of the supply in our home is 230. And if you want to represent this in and time domain or instantaneous, then you take the supply as Vn of t, then it has to be referred by Vp into sine omega t, where omega has a frequency information, that is 50 hertz. Then 230 is the RMS value, and we know that is equal to Vp by root 2. From this you need to find out Vp. What is that Vp? Root 2 times your V effective or VRMS hereafter. Getting everyone? All of you getting?
Yes,
So
sir.
VRMS of a pure sine wave is its peak value by root 2. If its peak value given, you can comment on its effective value or RMS value. V effective or VRMS. If VRMS is given, you can comment on its peak value as root 2 times VRMS. Then the instantaneous waveform of your AC signal, if needed, will become 230 into root 2. Getting everyone? Because VRMS is 230, okay, and into root 2, okay, into sine 100 pi t, okay, volts. That's how we need to represent our signal, AC signal energy, AC energy or AC source, okay, exciting our home, a single phase AC source. Getting everyone? All of you getting?
Yes, sir.
Yes, any doubts? Anyone having doubts till this point? Sendil, following this? Bhuvanesh? Yes, Kribagaran? Okay, we'll go ahead. Okay, so the important point is given. So why we have a convention of AC source referred by its effective value, that is nothing but our well known, okay, root means square value. Okay, so it's a square means nothing but squared average. Okay, so it is going to exist, normal average doesn't exist for a pure sinusoid, so we go for the squared mean or squared average, then apply the root. That is the one responsible, okay, to make the effective value of AC source as effective, or it is going to make the value for AC source which is as effective as your DC source. So we call it as V effective. Okay, with the common sense, it's VRMS. Okay, mathematical sense. Okay, understood? Fine, clear, everyone?
Yes, sir.
Yes, Fadil, it's everywhere. The moment I say 230, it's by default RMS. If I say 100 volt AC, what is that 100 volt AC? Unless and otherwise it is said as peak value, by default one should take it as RMS only. Getting Fadil? Getting it? Okay. So by default, the moment I say AC source, you need to take it as RMS value only. Okay. Say for example, I'll say an AC source. I won't mention the plus and minus also. Then I will simply say it's a 100 volt AC source. I will say 100 volt AC source. Then I will ask what is the power delivered by this AC source to the resistor. Resistor is equal to, say for example, 50 ohm resistor. Tell me what is the AC source, AC power delivered by the AC source. I'm asking what is the power delivered by the AC source. Simple example. I don't put plus minus.
100,
Yes, what's the power delivered by the AC source? 100,
200.
200. Okay. So the AC power means it's average power. That's only the effective power. Okay. So that is nothing but V square effective. It is directly connected across your resistor. So then it is R. That's all. So directly we can say the AC power or average power delivered to the load or delivered by the source. When you say with respect to source, delivered by. When I say with respect to the load, delivered to. So use delivered by and delivered to depending on which element you are referring. Okay. So it's average power delivered by the source. It's average power delivered to the load or absorbed by the load, we can say. So it is equal to V square effective by R. Directly it is 100 square divided by your resistance, that is 50 ohms. Yes, it is going to be 10,000 divided by 50. So that's your answer. So it's 1000 by 5, which is going to be 200 watts. Like that we can make the calculations easily. Okay, that is irrespective of this polarity marking. It can be this way or it can be this way, no problem. Understand everyone? Why no problem with respect to sign? Tell me why no problem with respect to sign?
Squared, sir.
Yes, because V effective is V square effective is what? 1 by T integral 0 to T. So this is your V in of T. It can be top positive, bottom negative, or top bottom positive, top negative. It is going to get squared. Therefore, automatically the negative sign will vanish. Always it is positive. Getting everyone? Yes or no?
Yes, sir.
Yes, sir.
So V square effective is always positive. Therefore, no problem with the sign. It can be plus. So don't get surprised if someone is asking if the source is, if an AC source of 100 volt, okay, shown like this, is delivering a power of, okay, some resistor I'm saying. An AC source shown like this in the circuit is delivering a power of how much? 200 watts. Then what power this setup will deliver? Don't say minus 200. Getting everyone?
Yes, sir.
So both are going to deliver
200 watts.
same power. Both are going to deliver same power. Yes, this is tricky. Okay, right? But the point, the concept lies in understanding of your V effective, because it's only just V in of T. When it comes to effective, when it comes to the one who is responsible to deliver the power is V square effective, and V square effective is going to have V in square. That is enough. Irrespective of this polarity marking, it is going to deliver same power. Getting everyone? Yes or no?
Yes, sir.
Okay, yes, it may be a simple interview to understand, okay, to check your understanding on the effective power delivered by the AC sources. Okay, this delivers 200 watts plus only. This also delivers what? 200 watts only. Even though you swap the polarity markings, the power delivered by the AC source remains same. Power delivered by the source is not going to be negative here. Okay, it is delivering positive power only. When the power is negative, what it mean? When the power is negative, what it mean? I am talking about power delivered. When you give the answer as negative, what it mean? You are saying that it is absorbing. The source is absorbing the power. When you say power delivery is negative, it is equivalent to it is absorbing the power. Is this point clear, everyone?
Yes, sir.
Okay, yes. So the source will, already we concluded whether it is positive of cycle or negative of cycle, it is always going to deliver power, means it is not sign sensitive. So top can be positive or top can be negative. That's not an issue. It is going to deliver always power. So it is delivering always power means it should be a positive number only. It should never take a negative value. Hope it is clear.
Yes, sir.
Yes, sir.
Okay, yes, that's another important fundamental. Then now answer this example. Next example. I'm going to connect two sources in series. This is a 100 volt AC source. This is a 50 volt AC source. Both are having identical frequencies. Identical frequencies. I'm putting plus minus and plus minus. and connect it to a resistor. Resistor of 50 ohms. Tell me what is the power delivered to the resistor? What is the power delivered to the resistor? Power across resistor, or AC power delivered by the source, or average power delivered by the source or to the load? Tell me what is the power delivered?
450 watts.
Yes, Yashwant, how much?
450
450? 450
watts.
watts, huh?
Yes, sir.
450 watts, yes. Anyone can confirm?
Yes, sir. Same, sir.
Same, okay, yes. One more response, please. Yes,
Yes,
Akshaya. Yes, Fadil.
450 watts.
450 watts. Okay, how have you made it? How have you made it? You just added the two values. This is V in 1, I can say, and this is V in 2, I can say. V in 1 is 100, V in 2 is 50. So probably you calculate the average power as 150 square by 50, correct? Am I right, Tejal?
Yes, sir.
What is that number? 150 square by 50. So 150 into 150, you know, to depend on a calculator. So 50 and this will be 3, then resulting in 450 watts. Yes, play like this. Even during examination, don't depend on your online calculator. Okay, do it manually quickly. So 450 watts. Everyone agree with this? Agree with this? All of you getting? Yes, Monisha, following this.
Yes, sir.
Okay. Then I'm calling this as a source Vn. The net sources, this is Vn. So tell me what is Vn effective. Anyone tell me what is the net source effective? This is my Vn. The total voltage I'm calling it as Vn. This is Vn1 and Vn2. Tell me what's effective value of Vn that is responsible for this power. I'm just asking. So what is the effective value of when two sources are connected like this? Tell me what is its effective value. My problem is only this. I'm asking only this. So when I have two AC sources connected like this, what is its effective value? That's where the problem goes to. It's plus minus. This is 100 volt with a frequency omega, and this is 50 volts with the 50 volts, right? With the frequency omega. 50 volts with the frequency omega. I'm asking what is the effective value of the source, V effective of this series combination. Yes. Yes, agree
150.
everyone? Can you say V in 1 plus V in 2? Yes, Yashwant?
I think so, sir.
Okay. You have to be confident, right? There should not be any dilemma. So 100 and 50, 100 plus 50. Do you want to say it's 150? So with this only we concluded, if you commit a mistake in this V effective, that is nothing but the net RMS value of your supply. When I add two AC sources like this, the net RMS value, if you make any fault with the net RMS, definitely you will make a fault, because by using this only you're going to calculate your average. All of you getting? Yes or no?
Yes, sir.
Then you, to clear your doubt, and take this as V in 1 of t, it's V in 1 of t, and this is V in 2 of t, and the two sources are in series aiding. Therefore, V in of t is equal to what? V in of t equal to V in 1 of t plus V in 2 of t. And be confident, okay, by doing this. Okay, that's a proof. That's a mathematical proof. It's aiding because plus minus, it's aiding. The two sources are in series aiding. Okay, just add them. Then you know what is it, the peak of V in 1? It is 100. What is the peak value? It's RMS 100. It's RMS 50. So go with their peak values. So then V in of t is equal to V in 1 with a peak of 100 root 2 sine omega t. Agree everyone? Getting? Yes
Yes,
or
sir.
no? Then second one, 50 root 2 sine omega t. Because they are just in aiding, series aiding. So just add them. Therefore, V in of t can be concluded as, yes, tell me what is the net V in of t now? V in of t, sin omega t is common. 100 root 2 plus 50 root 2 will become 150 root 2 sine omega t. All of you clear about this? Volts. All of you getting?
Yes, sir.
Yes, sir.
So this is V in of t. Tell me what's the peak of V in of t? 150 root 2. Therefore, tell me what is V in effective. That's your V effective of this net combination. What is that? Vp by root 2. Then what do you get? Ineffective. What is Vp? 150 into root 2 by root 2, root 2, root 2 will get cancelled 150. Then you are right. Getting all of you?
Yes, sir.
Yes, that's a proof. You need a proof. You need proof as an engineer for everything. Okay. Getting Yashwant now?
Yes, sir.
So this is the clarity you need to give yourself. Okay, when you add two AC sources, okay, by putting them in series aiding position like plus minus, okay, plus minus, then this is what your result is. Then simply you can add the two RMS values. Simply you can add the two RMS values. What is the condition? They should have identical frequency. All of you getting? They should have identical frequency. Correct? Then only the sine omega t can be kept common. If frequencies are different, if it is omega 1, if it is omega 2, can I take sine omega 1 and sine omega 2 common?
No, sir.
No, yes, that's a condition. Yes, we should know. So many facts only under the condition. Yes, condition must be known first. So this is valid. You can just add the RMS value of two AC sources connected in series, provided they should be in series aiding, and then provided they should have identical frequencies, then you are free to add them or subtract depending on aiding or opposition. Depending on aiding or opposition. Getting everyone? Getting all of you? Following right?
Yes, sir.
Yes, Swati following.
Yes, sir.
Dinesh following right.
Yes, sir. Following, sir.
Then you can answer this. Take this example as well. So then you can quickly give the answer for this. Same example, but plus minus, but minus plus. Now tell me what is the, this is I'm calling it as V in of t. Tell me what is its effective value. Give me V in effective. So this is 100 volt AC source with omega, and this is 50 volt AC source with
Sir, it's same as the previous.
same as previous, but I put minus plus.
No issue, sir.
Getting? Are they aiding or opposing?
Opposing.
Opposing. Because minus minus. Okay, it's like this. I have a 10 volt battery and then a 2 volt battery. Tell me what's the net value of this? This is plus minus and this is minus plus. Opposition, what is the net difference?
8, sir.
8 volt is the difference. Okay, you can take this as reference and the middle point will become minus 2 and add 10. This is going to become 8 and the top is 8. The bottom is 0. The difference is going to become 8. Like that one can conclude. A same way you can take this as a reference. Then it is going to become minus 50 and potential rises by 100. It is going to become 50. Getting everyone? Yes.
Yes, sir.
So V in effective is going to be 100 minus 50. Then it is going to be V in 1 minus V in 2 play. Okay. For the proof, do like this. Okay. Yes. Because it is going to become minus, then 100 root 2 minus 50 root 2 you will get. That result is going to be 50 root 2 and 50 root 2 is the peak. Make it RMS or effective. Then V in effective is going to be 50 volts only. Getting everyone? All of you clear about this? Yes or no?
Yes, sir.
So now I'll give this example. An AC source plus minus, a DC source plus minus. Find its effective value. That's what I'm calling it as V in of t. So what is the V in effective of this DC plus AC combination? Next example. So let this is an 8 volt AC supply. This is a 6 volt DC supply. This is AC. This is DC. Yes, clarity given. AC of some frequency. DC there is no frequency. Omega is equal to 0. Yes, V in effective or V in RMS. V in RMS or V in effective is equal to what? Yes. That's your problem. Yes, you can give the answer. It seems like they are series aiding. Okay, you can treat this as signal 1, V in 1 of t, and treat this as signal 2, V in 2 of t. You can happily go with the equation V in of t. Instantaneous voltage V in of t is equal to V in 1 of t plus aiding, so plus V in 2 of t. Getting everyone? All of you getting? Then V in of t will become V in 1 of t is 8 RMS. This RMS effective value. Therefore, 8 root 2 sine omega t, omega not given, plus the DC value. That is always a constant 6 volt. Yes, this is my signal. I'm asking its RMS value. I have a signal 6 plus 8 root 2 sine omega t volts. What is its RMS value? That's what I mean. Yes. 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 Anyone can give the answer? Yashwant?
Doing so.
Okay. Yes, that's only route. That's a way to play. Yes, try and give the answer. Take a minute. Yes, anyone got the solution?
14, sir.
1 4. Tejal?
Yes, sir.
So 8 plus 6. Correct?
Yes, sir.
Okay. Yes, Yashwant?
It's not
No idea.
possible to add AC and DC. Sir.
Okay. So how you conclude that, Swati? Who said not possible to add AC plus DC?
I'm sure.
Okay. Yes, that is the expression anyway. The expression is clearly mentioned. That's your V in of t. How can you give this result as 14? That's a question to be answered. Getting Tejal? It's RMS only I'm looking for. I know V in of t. I know the instantaneous signal representation. I want its RMS value. Yashwant, any answer you got?
No, sir, I'm confused.
Confused. Yes. That's the purpose of this problem ultimately. Okay. It is only to confuse and get clarity what to do in this situation. Yes, Sandil, what is your answer? Yes, Bhunesh? Yes, Fadil?
10 volts. I got.
You're getting 10. Fadil getting 10. Okay. Yes, Monisha, what is your answer? So if something new, you have to begin from the scratch. That's the purpose of giving all the fundamentals. You have everything. You need to start from that point. Okay. So what is known as we have the voltage source represented by V in of t is equal to DC of 6 volt AC of. So let me write it as 6 plus 8 root 2 sine omega t. That's all. Volts. Okay, that's my signal. I need its effective value. By default, as per the V in effective fundamental, it is root of what? 1 by t integral 0 to t V in square of t into dt. Agree everyone?
Yes, sir.
That's your square, that's your mean, that's your R. By default, we need to go for this RMS. Understood? Irrespective of signal, what signal you are playing with, that's a fundamental. That's a fundamental support. You already have it. Okay, then that's RMS. V in RMS or V in effective. That's what it means. So that is equal to whether you go for the square. If you go for the square, you don't need this root. Okay, getting everyone? Clear? Following right?
Yes, sir.
Then square your signal. Do it. It's periodic. This is again periodic. Can you plot? Anyone can plot the signal V in of t. If you plot this signal V in of t against time, it is going to have a DC value of how much? How much? 6 volt. That's a DC level. And then the AC is superimposed over your DC. Then it is going to be a 6 plus, yes, something like this. Okay, I don't know whether it is going to have a negative value or not. That's how it is going to be. Okay, it is the what is the peak? 6 plus 8 root 2. Negative peak? 6 minus 8 root 2. Getting everyone? So definitely it will have a negative value. Understood? All of you getting?
Yes, sir.
So it will have a negative value. That is a negative value. I'm just representing the waveform. That's all. Okay. So don't take this time axis as a zero axis for the voltage. So this is a negative voltage. So what is the peak of the 6 plus 8 root 2, please? What is that number? 6 plus 8 root 2 will be the maximum of the signal. 6 minus 8 root 2 will be the minimum of the signal. That's all. That's where your signal is going to be. That's your signal V in of t, the time domain representation of your input signal. Hope it is clear. Yes. Yes, right.
Yes, sir.
So we need this, its RMS value only. Yes, then as per the fundamental, let us go for V in square effective, then 1 by t integral 0 to t. Then V in square of t is going to be 6 plus 8 root 2. Let me take it this way. So let me take it formally as VDC plus VAC the whole square okay, into dt. Agree everyone? All of you getting?
Sir.
Then what will be the resultant of this? A DC plus AC combination will lead to what V in effective. Okay. Then this is equal to 1 by T. Yes. Yes. What is the first component of this squaring? 0 to T. What? V square DC into dt plus integral 0 to T 2 times VDC into what? VAC into dt. Getting? And third component integral 0 to T. What is that? V square AC into dt. Agree all of you?
Yes, sir.
Basic mathematics. A plus B whole square, A square plus B square plus 2AB. Okay. So I'm taking it as A square plus 2AB plus B square. Okay. So after expansion, yes, then integration comes for each term. Okay. Then tell me what is 2VDC into VAC. Okay. So let me take it to the next page. So then V in square effective or V in square RMS will be equal to 1 by T, then integral 0 to T V square dc into dt plus 0 to the integral 0 to T V AC square into dt. This alone will stay. Reason is that integral since 0 to T, integral 0 to T 2 times VDC into VAC of this integration is going to vanish. This integration will vanish. Tell me why this integration will vanish. So it is 0 to T 2 times VDC into what? This VAC is VP sine omega T into dt. Okay. So then instead of playing with the omega T, let us play with pi instead of T. Let me take this as 2 pi. That's one cycle. Instead of omega T, let me play with theta. Let me play with theta into d theta. Then tell me what is integration of sine theta?
Minus cos.
Fine then. Then what are your limits? Upper limit is 2 pi, lower limit is 0. Tell me what will be the resultant?
0, sir.
Minus cos theta. You're going to let the upper limit 2 pi, lower limit what? 0. Then what will be the resultant of this? Is equal to, getting everyone?
Yes, sir.
2 pi is nothing but 0 only for the cos. Cos 360 is cos 0, it is 1. So you're going to get, when you substitute upper limit, you'll get minus 1. Minus of minus cos 0 you will let, that is anyway going to be 0. Therefore, the moment you go for, what it mean effectively, it is a sinusoid. Okay, and averaging for one period. So a sinusoid area for one period will be equal to 0. Directly can make this as 0. That's the reason the second term is going to vanish. All of you getting this? Getting this point?
Yes, sir.
Okay, then conclude things. So only the d v square dc will exist, v square ac will exist. So tell me what is this? Tell me what is this? Okay, let me do it in the next step. So v in square effective is going to be this. So v in square effective is going to have only two components. One is 1 by t integral 0 to t v square dz into dt plus 1 by t integral 0 to t what? V in square, that is VAC, right? VAC square into dt. That's all. So tell me what is this? Agree? Yes or no? It's RMS value square of the AC component. Correct?
Yes, sir.
Then what about this? So V square dc is out of integration. Then V square dc is out of integration means integration of dt is t upper limit t, lower limit 0. Then you will get this 1 by t. Then this is going to be t upper limit t, lower limit 0. So you'll end up with this and this will get cancel is going to be this component. That's what v in square effective is. That's a proof. That's what you need to do if something is not known. Now you understand v in square effective is equal to what? V square dz plus v square ac. It's RMS. All of you getting? Yes or no? Getting this point? Yes, Yashwant?
Sir.
Tejal? Following?
Yes, sir.
Then tell me what is V in effective? V in effective is equal to root of V square dz plus V square AC. Shortly, V square AC means by default AC is represented by what? RMS only. Take it. So what's the DC signal? 6 volt. What is the AC signal? 8 volt RMS. All of you getting? Then square of them. 6 square is going to be 36. 8 square is going to be 64. Getting Swati?
Yes, sir.
Then root of.
Hundreds.
Answer is then.
10 volts.
Is it clear, everyone? All of you getting?
Sir.
Yes, Fadil. Is this your root? You said
Yes, sir.
10.
Yes, sir.
Is this your
is
root?
Yes,
Yes.
sir.
Yes, that's very important. Fundamental. When you combine AC plus DC, okay, you have to go like this. Okay, so that's a fundamental. Hereafter, you need not to go through this fundamental. Okay, this fundamental is universal. When you have two signals with different frequency, that's a root. When you have two signals, it can not to be DC, it can be AC also, but a different frequency. Two signals with a different frequency, by default, you need to go by their effective value square under the root sum of, okay, this is called VRSS effect, root sum square effect. This is called root sum square effect. That's what your effective RMS or effective RMS also. VRMS is nothing but VRSS. VRSS means, so go for the individual square of RMS values of signals. Sum them. First S refers your square. Second refers your sum. So it's sum square. Then root. Root sum square. Understood? All of you getting? All of you getting?
Sir.
This is root. This is your sum. And this is your square. So root sum square effect is nothing but your effective value or RMS value of the signal. Whenever the two signals are having different frequency, go by RSS concept. This is clear. This is called VRSS concept. Follow this when frequencies are unique for the signals. Hope it is clear.
Yes, sir.
Suppose, for example, an AC source, another AC source, it's given as 100 volt. This is given as 50 volt. It's plus minus, it's plus minus. Okay. So this is 100 volts, 50 hertz, and this is 50 volts, 100 hertz. And this is given as a reference. I'm calling this as V in of t. I'm calling this as V in of t. Now tell me, what is V in effective or V in RMS? Yes. Next example. Answer. Frequencies are different. Getting? If frequencies are same, what is the answer? We have done it already. All of you getting? What is the answer? What is the answer?
100.
150. Just addition. If identical frequencies, depending on aiding or depending on opposition, either 100 plus 50 or 100 minus 50. We got two examples, identical frequency. Now the frequencies are different. Frequencies are different. Yes. Immediately, already the concept is taught. Okay, go by this. And this is having frequency of 0. This is having some frequency. Frequencies are different means immediately go by RSS concept. Then the answer is by VRSS. So V in effective is equal to, yes, instantly you can say this. What is that? Root of
100 square.
root some square effect. Root of 100 square plus 50 square. Getting Dinesh? That's your VRMS value of the source. Yes. V in of t. Yes. Answer please.
111.8, sir.
111.8
8.
volts is your RMS value. Okay. There is no meaning if someone is talking about what is the peak value of this combined source. No meaning for that. Okay. Why we are calculating RMS? If I connect a resistor now, directly I can comment on the power. If R is equal to 10 ohm is connected, directly I can comment on the power dissipated across this. So purpose of V effective is only this. After getting V effective, if someone is asking you for this combination, what is the peak value? No, it doesn't make a sense. All of you getting? What will be the peak value? That is different. What is the maximum peak? Because you are adding two sinusoids which are having different frequency. Okay? All of you getting? And we don't know at what peak, okay, so at what theta they will get added will give the maximum. Okay, nobody, okay, so can quickly find that peak value. So problem is don't go from this RMS to peak. So here don't apply, RMS is known, so root 2 times RMS is our peak. No, don't do that. Okay, here don't say the peak value of the input is equal to root 2 times your RMS. Don't bring this concept into the play. It's not valid. All of you getting? All of you getting this point?
Yes, sir.
Okay. So you need to find out that peak just by adding this and find out the theta at which both can be added will result in a positive maximum or negative maximum. Okay. That you can find. Okay. But that is not equal to, that is not going to obey root 2 times this RMS because this RMS is based on VRSS, root sum square effect. Okay. So then if someone is asking you what is the power delivered to the load means, then the power delivered is equal to the V effective square or VRMS square divided by R. Like that you can calculate your power. Yes, divided by 10. 1, 1. So hope you have the answer. Answer square divided by R. Tell me that is the power. That's the purpose of going with V in RMS. That is the one responsible to deliver the power. Yes, what is that?
1,249.
1000?
249, sir.
249 point, Tejal?
924.
924.
Yes, sir.
924 watts. Correct? Agree? Everyone? Following right? Then the final example before the break. Hundred volt. I'll give a different example. 60 volt, 50 hertz, 100 volt, 1 minute, 80 volt, 100 hertz, plus minus, minus plus is connected to this effective source is connected to a resistor or load. 50 ohms. Find the power delivered to the load. Next example, find the power delivered to the load now. Power delivered or power across the 50 ohm resistor, not plus minus. Plus minus applicable only for the voltage. Is power delivered across. Power delivered to 50 ohm resistor is in the given circuit. Yes. V in 1, V in 2.
2 watts, sir.
2 watts, sir.
Yes, sir.
How we made Tejal?
Sir, same root, sir.
80 square plus 60 square or 80 square minus 60 square?
Plus only, sir. Plus
Okay. So then you made 80 square plus 60 square.
root of the answer.
Okay. What is that voltage? Effective?
100, sir.
Okay. Then make 5 ohms. Okay. Now what is your answer, Tejal? Instead of 50, make 5 ohms.
20 watts.
Okay. 20 watts is the power delivered to the load. Okay. That's one of the options. Okay. I'm not freezing this answer. Yes, you are free to give your version. You are free to give your own version. Yes, tell me your answers. Yes, Sendil, your answer, please. If I say V in of t, tell me what will be the expression for V in of t. V in of t, what will be the expression for V in of t? I'm taking this as plus minus. Here also this is plus minus. I'm just going with the V in 1 of t plus V in 2 of t. Tell me what is V in 1 of t? V in 1 of t is V in 1 of t is equal to 60 root 2 sine omega t. What about V in 2 of t? All of you. I'm just going by addition only, but actually they are not adding, they are opposing. Let me take V in 2 of t as negative. What is V in 2 of t? Minus 80 into root 2 sine. It's omega 1 t. And this is sine omega 2 t. Agree everyone? All of you getting? Following or not? Yes or no? Yes, Kribagaran? Following right? Yes, one can confirm by unmuting the mic. Monisha, following right?
Yes, sir.
Okay. So V in 2 of t can be written this way. But as per the fundamental, if we go to this, what exists finally is earlier VDC and VAC. In this case, instead of V square DC and V square AC, you will get V in 1 square and V in 2 square. All of you getting? Following.
Yes, sir.
And 2 V in 1, V in 2 will vanish once again. 2 V in 1, V in 2 will vanish like this. Okay, you try by this route. The first component square will exist. Second component square will exist. And the product of first component and second component will vanish. Okay, so prove yourself by taking this route. Therefore, the first component square, that's a positive square, will be positive. Second component, which is taken as negative, its square is also going to become positive. Therefore, the result is not going to change. The result is going to be the same. That is going to obey the RSS concept. If that is the case, then the result is going to be, yes, what is that? V in RMS is going to be, once again, irrespective of aiding or opposing, the result is same when we have two different frequencies. That's the beauty of this conclusion. Yes, what is that? It is going to be V in 1 square plus V in 2 square. It's by default RMS. That's what it means. It is 60 volt. It is 80 volt. Therefore, the result is going to be root of 60 square plus 80 square. Getting everyone? All of you getting? Following?
Yes, sir.
Yes, the result is root of
10,000.
10,000 is equal to 100 volts is your effective RMS value. Effective value or RMS value. Again, it is obeying the RSS concept. Okay, V in by RSS concept. Okay, that's a net V in. That is the one responsible to deliver the power. Then this is correct. Then you can go with the power dissipation. Power dissipation is equal to your V in square. That's RMS by default by R. What is V in square? V in is 100 volt. 100 volt square by your resistor. That is 5 ohms. Check once your answer.
Yes, sir. 2,000 watts.
Different watts,
Understood?
Yes, sir.
Rachel? Yes. 2000 watts. Yes. That's your answer. 2 kilowatts. If it is given in kilowatts, 2 kilowatts is the power delivered to the resistor. Getting everyone? Getting Monisha?
Yes, sir.
Swati getting this?
Yes, sir.
Okay, yes. So with this, we'll conclude this session. Have a break for 20 minutes. We'll begin. Okay, so with a few more fundamentals. So what is the point? So when frequencies are different, aiding and opposing doesn't matter. Go by RSS concept. All of you getting? If frequencies are different, aiding plus minus doesn't matter. Then in order to show plus minus, I can simply give something like this. I won't show the plus minus. Okay, don't expect it. The moment I connect two AC sources, okay, this is 60 volt, 50 hertz. Then this is 80 volt, 100 hertz. Don't expect plus minus. Then straight away, its effective value is equal to, its effective value is equal to 100. That's what it means. Getting everyone? All of you getting?
Yes, sir.
Yes, sir.
So don't expect plus and minus. Irrespective of the plus and minus, the result is obeying the VRSS concept. That's all between the 2 points. Okay, that's all. Even it can be given this is minus and this is plus, not a problem. Still, that's your VRMS. Okay, clear, everyone? It's clear. Hope it is audible, everyone.
Yes, sir. Yes, sir.
Okay, so with this, let me conclude the session. So we'll meet after 20 minutes. Okay.